Okay, welcome back. So now we're going to, we already finished the electrical circuits, and now we're going to start with the translational mechanical system. As I told you at the beginning of the last lecture, translational means a linear motion. So I'm making a translational motion now. I'm going in a linear trajectory. So it is opposite of a rotational motion. So the translational motion is not rotational motion. So our title is Translational Mechanical Systems. So I will start again in the same manner. Remember electric circuits, we started with listing the electric circuit elements, and I'm going to start by listing the translational mechanical system elements. So the first element is the mass. So mass is shown by a block like this, and I apply to the mass a force from the outside, and we get the displacement. So here we are measuring the displacement from an equilibrium position here. That is the displacement. So what is the relationship? And I have the mass value equal to capital M. So what is the relationship between the force that we apply and the displacement that we get from the mass? We know that this is Newton's second law. So I have m times x double dot is equal to F. This is a terminal equation of the mass. And it says that mass value times acceleration has to be the force that you apply. So you apply a force to the mass, and then you get the displacement according to this equation. In a way, this is like the resistor, capacitor, inductor equations that we have written. These are the terminal equations of the mass element for the translational mechanical system. The second element is the spring. So we show the spring with a notation like this. Again, we apply a force and we measure the displacement that we get from the mass. And I have the spring constant K here. You might remember from your high school courses, physics courses, or from your freshman physics courses, that there is a the relationship between F and X is a linear one. So in this case, we have F equals to K times X. So the displacement that we get is linearly related to the force that we apply to the spring. And the final element, not the final element, but the second from the last, is going to be the so-called damper. So this is the friction model in our course. Okay? The damper element is shown in a similar manner. So we are going to show it like this, and I'm going to spend some time in order to be able to explain what this does. So this is the force we apply, and we get a displacement from the damper. So I get the displacement X here. In the friction model that we are using in this course, we have the friction coefficient B here. And in this case, the relationship between F and X is going to be F equals to B times X dot. So X is the displacement, and X dot is the velocity, and X double dot is the acceleration. So here, it is the force that we apply is going to be proportional to the velocity of the damper. So to damp is sönümlenme in Turkish. So damper is just in Turkish sönümlendirici. So this is representing the energy loss in a translational mechanical system via the friction. So it is similar to a resistor in an electric circuit. And unlike the friction models that you might have seen in your earlier physics courses, this friction model is linear in F and X. There is no nonlinearity here. In general, a more correct friction model would be that we encounter in the nature would be actually a nonlinear friction operation. So since in this course we would like to remain in the realm of linearity, we are actually going to be using this type of friction model. So the friction force is going to be proportional to the velocity of the object. So if the velocity is 0, there is no friction force that is applied onto the object. And if there is a non-zero velocity, there will be a friction force that is going to be applied onto the object. This type of friction model is called viscous friction. Viscous friction model. And this is related to some fluids. So we need to have a liquid somehow, and this is the friction forces that you encounter in a fluid or in a liquid. So suppose that you are in a pool, so a pool of water, and suppose that you are moving your hand in that pool of water. You know that if you actually move your hand very, very slowly in the water, you would see that you will encounter only very small resistance, okay? A very small force would be applied into your hand. But if you want to move your hand quite fast in the water, you would see that the force that you need to apply to move your hand in a faster way in the water would be much larger. This is like the viscous friction model. So it is related to the velocity of the object, and it is scaled, the friction force is scaled linearly with the velocity of the object. Okay? So what does this figure is showing here? You can think of a piston inside the liquid. So suppose that you have a piston and you are trying to push the piston inside the liquid. Suppose that the liquid is quite a thick liquid, a quite viscous one. Suppose that you are working with honey, for example, ball. Then you have a piston, or imagine a spoon inside the honey. Okay? In that case, you would know that in order to push the piston inside into honey, you have to give a lot of force. And if you want to push the piston quite fast into the honey, then you need to apply lots of force in order to be able to do that. On the other hand, if you want to push the piston quite slowly inside honey, so think that this is a cup of honey, and think that this is the piston. Okay? In order to be able to pull this thing, the piston has to move inside honey, so you have to spend some force. Similarly, in order to be able to push this to the left, then you have to apply some force to the piston. Okay? So this is the viscous friction model that we are going to be using in this course. So remember, there were 4 circuit elements, and actually there is a direct correspondence between these elements and the circuit elements. You really do not have to understand this correspondence, but this actually behaves like a resistance in the circuit. So this is energy spending here. Friction is spending energy, actually. And in circuit terms, this is a resistance. And spring would be an inductor, and actually mass would be a capacitor in terms of some sense of equivalence. And remember, there is also a transformer in the circuit models, and we have seen its mathematical model. And here we are going to see an equivalent in the translational mechanical systems. And in translational mechanical systems, the equivalent is nothing but something called a lever. All right? So this is a schematic picture of a lever, and I would here put some lengths here. So this is going to be L1, and this is going to be L2, and we are going to be applying a force here, the force F1, and the lever is going to convert that force on the other side to another force here, which is given by F2. And here, suppose that I call the displacement here of this tip of the lever as x1, and suppose that I call the tip of the displacement of this tip, right tip, or as x2. Okay? Then there is a linear relationship. So here you shouldn't be confused. F1 is the force I apply to the lever, and F2 is the force lever is applying to the outside world. Okay? F1 is what I apply to the lever, and F2 is what the lever is applying to the outside world. So here, when you talk about forces in mechanical systems, you should always think about which agent is applying to the force to which agent. Okay? So here, I am applying this force F1 to the lever, and the lever is applying the force F2 to the outside world. Now let us try to write the expressions for relating x2 to x1, x2, x1, and f2 to f1. Okay? It is always, at least in my mind, it is always easier for me to write first the x2, x1 relationship. All right? I always try to write that relationship first. It is easier for me. Suppose that there is a non-zero displacement of the lever. What is x2 going to be? What should I multiply x1 with to obtain the displacement x2 here? Of course, from the similarity of the triangles that we obtain here, x2 is going to be larger. Okay? When I actually shift or rotate the lever just a little bit, then x2 is always going to be larger than x1. So here the relationship between x2 and x1 is going to be this one. If L2 is larger, then x2 is going to be larger. Okay? And what about the force relationship? Force relationship will be having just the reverse coefficient here. Okay? So it is actually going to have L1 over L2. Sorry, you might have experienced a jump in the video here. My wireless microphone was running out of its battery power, so I had to change it. So now everything seems to be okay. So here we have written the terminal equations of the lever. So this is just like a transformer in electrical domain. So this is that transformer is the electrical energy conversion device, and the lever is a translational mechanical energy conversion device. So here I have x2 is equal to L2 over L1 x1, and f2 is just, I have just the reverse coefficient here, okay? L1 over L2. Why do we have this reverse coefficient here? Because of the conservation of power or energy, you can say. If I multiply f times x2, this has to be if I multiply f2 and x2, this should be equal to f1 times x1 in order for the conservation of power here. That is why we always have reverse coefficients here. And just write whichever is you remember better. In this case, this is this x relationship for me. And then if you find this one correctly, you always know the other one by reversing the coefficient here. So this is the lever model, and here I'm going to say one more thing here, and that is about the friction. So we usually we can show the friction with this damper element, and sometimes we don't put any damper element, but we just show it in this manner for a mass. Okay? So this means that there is a damper here connected to the velocity of this mass. That also is going to mean the same thing as the friction damper element. And these are the elements of the translational mechanical systems. And we use the Newton's second law in order to be able to write the mathematical model. We use Newton's law to find the mathematical model. And what is the Newton's law? In this case, we are talking about the Newton's second law, and it is going to be m times x double dot is going to be the net force applied onto the mass. Okay? So we have m times x double dot is going to be net force applied onto the mass. Of course, writing this net force is going to be the most difficult thing in translational mechanical systems. This is nothing but F equals to m times a, m times acceleration. Okay? So we use this equation in order to be able to write our mathematical models. In our exposition, I'm going to be starting with a simple example, and then we're going to jump to a much more complicated example at the end. But first of all, I'm going to start with this simple example. So suppose that I have a single mass. I have the mass here, and there is a force applied onto the mass, and I have the displacement of the mass in the same direction as the force. There is a spring here with spring coefficient K, and there is a friction element here. There is a damper here with the friction coefficient B. All right? So here, as soon as you see this picture, you need to understand that this is the same thing as, so an equivalent drawing can be written as follows. There is this mass here. There is a friction here, that is B, and there is a spring here with spring coefficient K. And of course, I have the displacement and I have the force applied onto the mass here. That is the external force applied onto the mass. So these two models are exactly the same. In one of them, I put the friction in this way into the model here like this, and the spring remains where it is. And that is the only change between these two drawings, actually. So these represent exactly the same system. So what we have to do in this case is to find differential equation, transfer function, and state space representations. So as you see here, again, I started to talk about the representations of the system, mathematical models of the system. Again, this statement is really meaningless without something. So I have to know what the input of the system is and what the output of the system is for this statement to make actually any sense. All right? So here I'm defining my input as the force that is applied from the outside, that is F of t, and I'm calling the output, I'm defining the output as the displacement of the mass. Okay? It is x of t. So by using this input and output definition, we have to find the mathematical model of this system. Before I actually start, I'm going to be making a change here. So when I try to find the state space representation, I need to define the state vector, which is going to be called as x again. Okay? But there is an x here already. So in order to not get confused about which variable is which, I'm going to change this displacement variable to y instead of x. Okay? So that I don't confuse this displacement variable with the state vector. Okay? So similarly, I will change the output to y of t, the same displacement that we have. Okay? So now let us try to obtain the first differential equation representation. Differential equation representation always comes first before we try to obtain the transfer function and state space representations. So here we are always going to be starting in the same way. When we try to obtain a differential equation representation, I am always going to be starting with an m times acceleration. Okay, so this is the acceleration, and here, since I call the displacement to be y here, it is going to y double dot. This y is the displacement of this mass from its equilibrium position. Okay, so the mass is initially at the equilibrium, and but when I change it to this way, what displacement is positive, and when I change the position of the mass in the other way, the displacement is negative. So this is m times y double dot, which is the m times the acceleration of the mass, should be equal to the net force applied onto the mass from the outside. Okay? So what can apply in the direction of increasing y, of course? I need to count forces in that direction, because this is y direction is in that direction, so I need to count forces in this direction. If I have a force applied in the other direction, then I will, if F is pointing in this way, then I need to add here minus F. Okay? Because I need to always count the forces in increasing y direction. So now what can be the outside forces applied onto this mass? One is this external force. It is the input force applied onto the mass, and it is applied from outside. And it is in the direction of increasing y. So I put F here. Okay? This is the input force applied. Is this all? So, is this all that is applied onto the mass? The answer is simply no. Okay? So, spring also applies a force onto the mass, and the friction is also applied onto the mass. Okay? So now let us look at the spring. So suppose that I make the mass come to the right just a little bit, okay, from its equilibrium position. Suppose I pull the mass to the right just a little bit, so that y is now positive. The displacement is positive. In that case, I know that the spring is going to pull the mass in the reverse direction. Okay? So when I bring the mass from here to here, then y is going to be positive, and spring is going to pull the mass in the other direction. So spring is going to apply a force onto the mass towards the left. All right? So what is going to be the magnitude of that force? It is going to be k times y, but its direction is going to be towards the left. Okay? That is why I'm going to put here k times y, the force applied onto the mass by the spring. Okay? The reason for the negative sign here is that when y is positive, when mass is taken from here to here, then the spring is going to pull the mass towards the left with the force magnitude k times y. But since the direction of that force is going to be towards the left, in the opposite direction of increasing y, I'm going to be putting a minus here in front of k times y. Okay? So what happens when, so this is actually the correct model, even if y is negative. Okay? What happens when y is negative? Then I take the mass from here to here. Okay? Then what would happen is that y would be negative, and K is positive, then this is negative, positive, negative. There will be a positive force applied onto the mass. And that force is going to push the mass in the increasing Y direction. But that is what is going to happen with the spring, right? If I squeeze the spring a little bit in this direction, then the spring is going to apply the mass, a force in the increasing Y direction. Okay? That is what happens with this model. Negative and negative will make positive, which means that force is applied to the right. Okay? I'm sorry. So here, the only thing remaining here in this model which is missing is the effect of the friction. Okay? So now I know that the friction is going to be related to the force and the friction. The friction force is going to be related to the displacement with this equation. Okay? So the friction force is going to be B times the velocity of the mass. All right? So now we're going to actually be able to add the friction force into the equation here. So in order to be able to add that force, suppose that Y dot is positive. Y dot is positive means that mass is moving to the right with some velocity, okay, with some speed. If Y dot is positive, then the mass is moving to the right like this, okay? In that case, there will be a friction force due to this damper, and this damper is going to be applying a force to the mass in the direction like this, towards the left. All right? So this force is going to have the magnitude B times Y dot. But what about the direction of that force? If Y dot is positive, the friction force, the mass is going to be moving in this direction, and the friction force is going to be in the opposite direction of the movement. And that is why I need to put here another minus sign. What happens if the mass is moving in the other direction? If in that case Y dot is negative, so mass is moving towards the left, and the friction force should be in the opposite direction again. But this is what this equation is already telling us. If Y is negative, then negative and negative makes a positive, so the force is going to be in the direction of increasing Y. Okay? So everything is okay with this model. And these minus signs are coming here because both the spring and the friction applies a force onto the mass in the opposite direction of movement. Okay? If Y is positive, spring pulls in that direction. If Y is negative, then spring pushes in that direction. And if Y dot is positive, friction is in this direction. If Y dot is negative, mass is moving towards the left and the friction is in the opposite direction. These minus signs are appearing just because of that. All right? So then this is my differential equation representation. So we see that this equation includes the output Y, and I have the output Y, and the input F here. All right? So this is our differential equation representation. And actually, once we obtain this representation, the other representations are easy. So now let us go into transfer function representation. In that case, I need to calculate a Laplace domain quantity G of S, and this is going to be the ratio of the Laplace transforms of the output to input. In this case, the output is the displacement Y, so this is going to remain, this is my definition, and the input is the force, external force applied onto the mass, and this is going to be F of S. So instead of U of S, the Laplace transform of the input, I'm going to put here Laplace transform of the force F of S. Okay? So from this equation, it should be easy to actually calculate this ratio, which is going to be my transfer function. So let us pass this equation into Laplace domain, and remember, in this case, I need to assume that all initial conditions are equal to 0. That means that y of 0 is 0, so initially the mass is at rest, meaning that its initial displacement is 0, and y dot should be equal to 0. So initially the mass should have 0 displacement, 0 velocity. Okay? So now let us go into Laplace domain. M times Laplace transform of y double dot is s square y of s. So remember, when initial conditions are 0, second order derivative is just multiplication with s square in Laplace domain. This is equal to f of s minus k times y of s, linearity of the Laplace transformation, minus b times, instead of y dot, I will write s times y of s. Then I will collect all of the output terms on one side. So ms square plus bs plus k times y of s is equal to f of s. Okay? Let us now calculate this ratio. Take f to the left and take this term to the right. Then transfer function is going to be given to us as 1 over ms square plus bs plus k. Okay? So this is the transfer function representation of this system. So think about the order of this system. What is the order of this system? You can either look at the differential equation representation and tell me the largest derivative order here, or you can look at the transfer function and you can tell me what the highest power of s we have in that transfer function. Okay? So both of them should be equal, and we have a second order system in this case. So depending on the poles of such a transfer function, we are going to have a different behavior from the mass spring system. So now the only thing remaining is the state space representation. In the state space representation, I need to start with a state vector definition. Okay? How many state variables would I need in this case? We know that the number of state variables that is necessary to obtain the state space representation is the order of the system. And in this case, the order of the system is 2. As a result, I need to use 2 state variables. So probably you might have guessed currently which variables I am going to choose, because we have a very similar differential equation that we have obtained in the earlier examples. So you can think that we need to have y here, and if I put y here, then in the state space representation, I need to be able to express the derivative of y, which is y dot, as a linear combination of the state variables plus the input. So in order to be able to express y dot as a linear combination of the state variables and the input, I need to add here y dot as a state variable. Then as soon as I add y dot as a state variable, then I need to be able to express derivative of y dot as a linear combination of the state variables and the input. Then the derivative of y dot is y double dot. And how can I express y double dot as a linear combination of these state variables plus the input? And the answer is easy here. In this differential equation, y double dot is expressed as a linear combination of input plus the state variables. Okay? So this differential equation can be used in order to be able to express y double dot as a linear combination of the state variables and the input. So now let us write the state space representation. X dot is, I have a times x plus b times u, and y is equal to cx plus du. So now x is given here. It is y and y dot. And x dot is going to be y dot and y double dot. Okay? And here the input u here is nothing but the force F. Okay? That is defined to us. And the output is nothing but the displacement y. Alright? So now let us try to fill in the missing matrices and vectors. So I have here the first element of x dot is y dot. I need to express y dot as a linear combination of y dot, and f. And these are going to be the coefficients that are necessary. And then I need to express y double dot as a linear combination of y dot, and f. And in order to be able to do that, I will go back to the mathematical model, differential equation representation. And I need to express y double dot as a linear combination of y dot, and f. What is going to be the coefficient of y in that expression? Express y double dot as a linear combination of y dot, and f. What is the coefficient of y in that expression? It is going to be minus k divided by m. Okay? Minus k divided by m. And what is the coefficient of y dot? It is going to be minus b divided by m. And finally, what is going to be the coefficient of the input in the expression of y double dot? And y double dot, the coefficient of the input f in y double dot is 1 over m. I can divide both sides of this equation with m, and then everything would be clearer. Okay? And then I would put here 1 over m. Okay? So we have found the A and B matrices here, and now the output equation is much easier. I know that the output here is the displacement y, and that means the first state variable. If I want to get the first state variable into y, I put here 1, 0, and I put a 0. There is no input contribution in the output. In some systems there might be input contribution, but here, in all of the examples that we have considered before, the output is one of the state variables. As a result, we didn't need to use any input coefficient here, d. It was always 0. But this matrix, this C vector, was composed of all zeros except for a 1 at one of the places. And that was because the output in all of the examples that we have considered was one of the state variables. Okay? That was why we obtained this type of C vectors. So this actually completes this example. Now we're actually going to go into a much more complicated example. So maybe I should draw it here. So I'm going to start with a lever here. Maybe I should draw in a better way. So this is the lever here, and the lever is just connected to a stationary point. This notation just shows a stationary point that is not moving at all. And then we're going to have two masses. I will have one mass here and another mass here. This mass is called M1 and this is called M2. And I have here a spring, and I have here another spring. Okay? And I have here a damper, and I have some frictions at the bottom. Okay? Let us give these components some coefficients. So I will have here spring coefficient K1. I will have here the friction coefficient B1 and B2. I will have here a friction coefficient B3, and I will define some displacements here. So this is going to be the displacement X1. This is going to be the displacement of the second mass. That is going to be X2. And the spring has the spring coefficient K2. All right? So let us complete the lever here. So this length is defined to be just 1. Okay, the length is just 1 meter here, and I have this length is called just gamma. Okay, the displacement of this tip of the lever is called x3, and displacement of this tip of the lever is called x0. Okay, maybe I should erase the output equation from here for it to be more visible like this. Okay, so this is our system, and what we would like to do is again obtain the differential equation, transfer function, and state space representations. So here again, what is missing is the input and the output definition of this system. So I'm first going to be defining that. So the input is the displacement x0, okay? So externally we are displacing this end, this tip of the lever, and the output is defined to be the displacement of the second mass. It is just x2, all right? And we have to find the mathematical model for this system. So this might really look scary at first sight, but once you get the main idea, you will see that it's not really difficult to write the differential equations describing this type of system. So here, before I continue with obtaining the differential equations, I'm first going to try to explain why can we have this type of mathematical model. So here, you see some springs here. In general, of course, we might need some springs in some mechanisms, but most of the times, springs are put into mathematical models to model elasticity. Okay? So somehow, a spring here connected to the mass means to me that this mass is in some way elastic. So there are two masses in the actual world, and the first mass has some elasticity, and this is modeled by this spring, putting a spring here. All right, and similarly, the second mass has also some elasticity, which is modeled by the spring K2 here. Both of the masses have some frictions of their selves. So this is the friction of mass 1 with the ground here, and friction of mass 2 with the ground. And here you see that there is a lever connected between these two masses. What does that mean? So you might understand that if both of these masses are moving with the same velocity, then this damper is not really squeezed, or it is expanded. Okay, so if both of the masses move with the same velocity, the damper is not going to apply any force to any mass. Okay. So therefore, what is the purpose of such a damper? This damper is modeling the friction between these two masses. If these two masses move relative to each other, then there is going to be a friction force applied to both of the masses. Okay? If the velocities are not equal for these two masses, then there will be some friction force, and there will be some energy loss in the system. So this is the mathematical picture of this system. If I want to draw another picture of these two masses, which is closer to the reality, I would just draw something like this. This is mass 1, this is mass 2, and this mass is just elastic. Okay? And there is a lever here touching this mass. Let us say that it is something like this. and this mass is just elastic, okay? And which is modeled, the elasticity is modeled by this spring, okay? This mass has some friction here, which is B1 with the ground, and this mass has some friction with the ground, which is shown by B2, and there is a friction between these two masses as well, which is modeled by B3 here. And what does this K2 represent? It represents, so this end of this mass is also elastic. So when I push it, it makes a spring motion. All right. So this K2 is modeling that type of behavior or that type of property. So what is happening in such a system is that I change the tip of this lever here, and this lever, which I can assume that it's a rigid body, and it is touching the elastic part of mass 1 here, and the elasticity is modeled by the spring K1, and there is a friction between the mass and the ground, which is B1, and the mass 2 and the ground, which is represented by B2, and if this mass moves relative to the other mass, then there is going to be a friction force applied onto both masses, okay? And this type of friction is modeled by a damper which is placed in between these two masses. So if the velocities of these masses are different, then this damper is going to apply a force to both of the masses, okay? So we really do not want to torture ourselves by putting here springs or dampers into places. Each of these components are modeling some physical phenomena. And the picture that you see here is an idealization of that phenomena, actually. Okay? So, but the actual picture might really look much more different than what we have in the idealized mathematical model here. All right. So now let us try to obtain the models for such system. So I will start with the differential equation representation. We always start the differential equation representation in the following way. I first write m1 times the displacement of the first mass, the x1 double dot. Okay? This is going to be the net force applied onto the mass. Okay? So I have here, this one is given like this. So I need to write here the net force applied onto mass m1 in the direction of increasing x1, okay, towards the right. All right. So on the right hand side, I need to have the force applied onto the mass m1 in the direction of increasing x1, increasing displacement. So now we have to be really careful. So in order to be able to write the external forces, here we see that there is no external forces to this system. From the outside, no force is applied. But here, onto M1, there might be some forces applied by the spring, by the friction, and by this friction element. Okay? So how can I express those forces? In order to be able to write those forces, I'm first going to be assuming that x3 is 0. Suppose that this tip of the lever is fixed. Okay? Suppose that x3 is always 0. Then how can I write the force applied onto the mass by this spring? Suppose that I pull the mass just a little bit to the right. Since x3 is 0, the spring is going to be expanded, and the spring is going to apply a force in the opposite direction of x1 onto this mass. And what is going to be the strength of that force? It is actually going to be k1 times x1. Okay? And actually, because the spring is applying a force in the reverse direction of x1, when x1 is positive, spring force is in the other direction, in the opposite direction, I will put a minus sign here. So this is what would happen when x3 was equal to 0. If this x3 was equal to 0, then when I pull the mass to the right, then the spring would apply a force in this direction. But what happens if x3 is not equal to 0? Suppose that x3 comes just a little bit also to the right. In that case, it is going to be important for this spring only the relative displacement between x1 and x3. Okay? So if x1 and x3 are the same, then the spring will not be expanded, or it will not be squeezed at all. So the spring force should be equal to 0 if x1 was equal to x3. Okay? If x1 is equal to x3, spring was neither expanded or it was squeezed. So the spring force should be 0 when x3 and x1 are equal. So what does this tell us about that equation? When x3 is not equal to 0, I need to put here x1 minus x3. I need to put here the relative motion, relative displacement between x1 and x3. Okay? So if x1 is larger, if x1 is larger than x3, then the spring is going to be expanded, and then there will be a force to the left. On the other hand, if x3 is larger than x1, then the spring is going to be squeezed. Okay? So the spring is going to apply a force in that direction to the right on this mass m1. So if x3 is larger than x1, then this is going to be negative, and negative times negative is going to be positive. This is going to be a force applied onto the mass to the right. Okay? So that should be the equation, that should be the term that we need to add about the force applied onto this M1 by the spring K1. Now I'm going to continue adding the forces. Let us look at the B1 force here, the friction force between M1 and the ground. In this case, do you think the relative motion, this is going to be a relative force or an absolute force? So this friction is due to the motion of M1, and this is motion between M1 and the ground, which is stationary. Okay? So therefore, we won't care about the relative quantities for this friction component. It is going to be, so how should I add that force? Suppose x1 dot is positive, then this mass is moving in this direction to the right. Okay? Then the friction force due to B1 is going to point in the reverse direction, and that is going to be, its strength is going to be B1 times x1 dot. Okay? But since when x1 dot is positive, the friction force is going to be towards the left, we're going to have here a minus sign. All right? And that completes the forces applied onto M1 due to K1 and B1 here. And the only thing remaining which can apply a force onto M1 is going to be this friction. Okay? And you might guess that relative quantities will be important for this friction term. Okay? So now let us try to apply the forces applied onto M1 by this B3. In order to be able to write those forces, I will assume that x2 is equal to 0 first. Suppose that x2 is equal to 0, and suppose that x1 dot is positive. So this mass is moving towards the right. if x1 dot is positive, velocity is positive, so mass is going in that direction. Suppose that x2 is 0, so this is fixed now, and suppose that this mass is moving towards the right. Then we see that this damper is going to be squeezed, which is going to apply a force onto M1 in the opposite direction. What is going to be the strength of that force? We know that the friction force are friction coefficient times the velocity. So I will put here B3 times x1 dot. Okay? So this is going to be the force that is going to be applied onto the mass M1 when x2 is 0, or when x2 dot is equal to 0. All right? So what happens if x2 is moving as well? If this thing is not stationary? So here you can guess that if both of these masses are moving with the same velocity, then this friction element is neither squeezed nor it is extended. Okay? That means that when the velocity difference between those two masses is 0, then there won't be any friction force. Okay? If these two masses are moving with the same velocity, then they will not actually encountering any friction force between them. Only if these two masses are moving with different velocities, in that case we are going to encounter a friction force between these masses. Okay? So here what should be the term? So the first thing that I put here is a minus sign. Okay? Because if x2 is equal to 0, if this mass is moving towards the right, then the friction force is going to be in the opposite direction. That is why I put a minus sign here. Then if x2 is not stationary, x2 is not equal to 0, in that case the relative velocity of the masses will be important in this mathematical model. So here I'm going to put here minus x2 dot. Okay? What does that model tells us? So if x1 dot is larger than x2 dot, then this mass is moving faster than this mass, which means that there is going to be a relative motion between the masses, and there will be applied a friction force onto M1 in that direction. Okay? If the difference is positive, force is in that direction onto this mass. What about the opposite behavior? If x2 dot is larger than x1 dot, in that case this mass is moving faster to the right. Okay? And when this mass is moving faster, then it is going to pull the other mass due to friction between those. Okay? And as a result, onto M1, a positive friction force will be applied in the increasing x1 direction. So if x1 is small, if x2 is larger, if x2 dot is larger, then this is negative, and there is a negative sign here, which makes the force positive, meaning that M1 is going to be pulled to the right by the friction between these two masses. Okay? So this is the equation for the first mass. Let us write the equations for the second mass. In order to be able to write it, I always start with m2 times displacement of the mass, and I have double derivative. Okay? So this is going to be the net force applied onto M2 by the other elements in the system. Okay? So now let us try to write the forces applied onto M2 in the direction of increasing x2. Okay? I will first start with B3 here. And I'm always going to be doing the same thing over and over. Suppose in order to be able to write the force on M2 due to B3, suppose that x1 is 0. Suppose that this mass is stationary. Okay? Then when this mass is moving towards the right, this B3 is going to pull this mass back, okay, to the left. That is why I need to have a minus B3 here times x2 dot when x1 is fixed to 0. But if x1 is moving as well, then what is going to be important is going to be the relative velocity between the masses. So you might actually see a trend here in these equations. When you write, if you start writing your equations in this manner, if you put here minus signs, then the first variable that is going to appear in the equations is going to be the own variable of the mass, okay? So if you put a minus sign here in front of the spring, I have always x1, which is the displacement of this mass, own displacement of this mass, which is appearing here. So similarly, if you put a minus sign here, it is always x1 dot that is going to be appear here. It is the own velocity of the mass m1. And if you do the same thing for this one, then if you put a minus sign in the front, then it is always going to be the own velocity of the mass. The velocity of mass m2 is x2 dot, which is going to be appear first in front of the minus sign. Okay? Let us complete the equations. Now let us write the force applied onto M2 by this friction B2. This is not a relative friction force. This is the friction between ground and the mass M2. So here, what I'm going to put here is going to be minus B2 times x2 dot. Okay? There is no parentheses and a relative minus something here, because the ground is always at 0 velocity. That is why I won't put any minus sign. You can just write here minus 0, which is the velocity of the ground, which is going to be the same thing here. And finally, I have the spring force applied onto M2 by this K2. Okay, and that is going to be, I put again a minus sign, K2, and is this going to be a relative motion or an absolute motion? In this case, this spring is between a stationary point and the mass. That is why here there will be only x2. Okay? So this was the most difficult part of writing these equations. I hope I could make it clear how you write these equations. So here, I always try to put minus signs here, and when you put those minus signs, it is always going to be the own variable of the mass that we are considering that is going to appear first. Okay? So here, the own variables are x1 and x1 dot. x1 appears first with the minus sign here, and x1 dot appears first with the minus sign here, and x1 dot here, it is always the first term. And in the second equation, if you write minus signs here, if you put minus signs, then it's always going to be x2 and x2 dot that is going to appear first in the relative motions. So here, x2 dot appears first, as you see. So does this complete the differential equation representation? In this case, the answer is no, and the only reason that I'm saying so is because here I didn't make any connection between with this lever here. So all I have written here is related to this part of this system. Okay? So currently I did not connect this lever into the system. And here let us try to connect that. So I'm going to write here the relationship between x3 and x0. That is going to be the final thing that I'm going to write in this model. So you see here that x3 is appearing, but this is neither an input nor a displacement variable of any mass. So I'm going to connect x3 with x0 as the final thing here. So what is the relationship between x3 and x0? If you remember the level equations, you can think here like that. So here, this is 1 meter, and this is gamma meters. Okay? Here I have actually drawn gamma to be smaller than 1. Okay? So now if you change the position of this lever, so which displacement is going to be larger and which displacement is going to be smaller? Obviously, I don't know if it is obvious now, but the tip of the lever with larger length is going to have a larger displacement. Okay? So here I can actually say that when this lever moves, x3 is always going to be the smaller one. All right? If gamma is smaller than 1, then x3 is going to be smaller than x0. So what does this tell you about the relationship between x3 and x0? So this is going to be just gamma over 1, which is just gamma times x0. If gamma is smaller than 1, then x3 is smaller than x0 always. And if gamma is larger than 0, then x3 is going to be larger than x0. Okay? If gamma is larger than 1, then, sorry, if gamma is larger than 1, then x3 is going to be larger than x0. So this completes the differential equation representation. Here, I won't work with on these differential equations anymore, and I will accept that this is the differential equation representation that we can find. Okay? Now let us go into the transfer function representation. In order to be able to do that, I will first get rid of this. And what is the transfer function? Transfer function is g of s, and it is the ratio of the Laplace transforms of the output to the input. In this case, the output is x2. So y of s is going to be capital X2 of s, and the input is nothing but x0. Okay? So u of s is going to be x0 of s. So I need to find this ratio in order to be able to find the transfer function of this system. And what I need to do is to use these equations in some way to obtain actually this ratio. Okay? It is not an easy task at this point. So let us try to do this. The first thing that I'm going to do is to pass all of these equations into Laplace domain. Okay? Because transfer function is a Laplace domain quantity, and as a result I need the Laplace domain quantities, and I need to pass both of these equations into Laplace domain by assuming that we have zero initial conditions. Okay? So let us pass the first equation into Laplace domain. M1 times x1 double dot is going to be s squared x1 of s. That is equal to minus k1 x1. Here, of course, I can write x1 of s. I can put parentheses and s's here. But you need to remember that all of these x1s, x2s are functions of s. So I will skip, for the sake of brevity, the s's here. x1 minus x3 minus b1. So here this is going to be s times x1, x1 of s. I'm not writing that s's anymore. So I have b3. From both of these there will come an s. So I will put it here. And then this is going to be x1 minus x2. Okay? This is the Laplace domain equivalent of the first equation, first differential equation. Let us write the second one. So it is m2 times s squared x2. I'm not writing parentheses s. Minus b3. From both of these terms there will come an s. And I have x2 minus x1. And minus B2, this is going to be S times X2. So you see that differential equations are turning into algebraic equations. So derivatives are turning into multiplications with S or S squared. Okay? That is why that is an algebraic operation here. The multiplication is an algebraic operation. Derivative is a differential operation. So differential equations are turning into algebraic equations when I go into Laplace domain. So I have minus K2 X2. And finally this last equation, it is going to be X3 is equal to gamma X0. Okay? So now what do I need for calculating this transfer function? I need to leave only two variables in these equations. I need to get rid of all of the other variables. These two variables need to be X2 and X0. So I need to get rid of all of the other variables here. What are those extra variables? X3. I need to get rid of X3. And what about X1? X1 is neither of these variables, so I need to get rid of it in order to be able to calculate the transfer function. Okay? So in order to be able to do that, I will actually try to collect all of X1 of S terms on the left in the first equation, all X2 of S terms on the left in the second equation. Okay? So I have M1 times S squared. This has X1 of S in it, so I take this multiplier here, the coefficient, and then I will take S terms. Then there is going to be a term here related to X1, and there is another term related to X1 here. When I take both of these terms to the left, it is going to be plus B1 plus B3 S. Okay, this is the multiplier of X1. This goes to the left hand side, it becomes B1S, and this X1 goes to the left hand side, it becomes B3S. Okay? Now, what about the constant terms? The X1 has a multiplier minus K1 here. I take it to the left as well. So that is going to give me a K1 here. This is going to be multiplied with X1 of S. And what about the remaining terms on the right? There is going to be a term here which is related to X3, okay? And while trying to transfer this equation to there, I'm going to get rid of this X3 and I will instead write gamma X0 instead of X3, okay? This minus cancels this minus sign, so this is K1 X3. So instead of K1 X3, I'm going to write K1 gamma X0. K1 gamma X0. Okay? What about the rest of the terms? I have handled this X1, handled this X3. I have already handled this one. I have already handled this one. The only thing remaining is this one. So it is minus signs are cancelling. So B3S X2 plus B3S X2 here. Okay? In the second equation, I'm going to do a similar thing. In this case, my variable is X2, so I'm going to collect all X2 terms on the left. Okay? X2 term, X2 term, X2 term here. So now let us write this. M2 times S squared, this term, and then I would have minus B3S here and minus B2S here. These are all X2 coefficients, and these are going to go to the left, which is going to give me this, plus B2 plus B3S, and the final X2 term is the constant multiplier here, which is minus K2. It's going to go to the left, which is going to be plus K2. and this is going to be x2 of s. That is going to be equal to what is remaining on the right hand side. So I have handled this term, this term. The only thing remaining is this. Okay? Minus signs are going to cancel. B3s x1. B3s x1. Okay? So now you see that I don't have to write the last equation because I have already taken care of that. Okay? So now in order to be able to write these equations in a simple way, I'm going to call this multiplier here as d1 of s. I'm going to call this multiplier as d2 of s. Okay? And then I'm going to write the equations in a simpler way. d1 of s, x1, is equal to k1 gamma x0. x0 is the input, remember. b3s, x2. And d2 of s, x2, is equal to b3s, x1. Now, in order to be able to calculate the transfer function, I need to get rid of all variables except for the input and the output. I need to get rid of all variables except for x0 and x2 here. So in these equations, I have only one extra variable, and that is x1. That is why I need to get rid of x1 in both of these equations. And then I need to cancel x1 from these equations. How can I do it? So you can actually extract x1 from the second equation, and then you can substitute it here. And that is going to give you an equation only in terms of x2, x0, and x2, which is going to be fine. So here is what I'm going to do. So instead of extracting x1 from here, I'm going to multiply the second equation with d1 of s. Okay? d1 of s, d2 of s. I'm multiplying both sides with d1 of s. x2 is equal to b3 of s, d1 of s, x1. Okay? This is nothing but multiplying the both sides of this equation with d1 of s. Okay? Now you see that I have d1 of s x1 here, which is this term. And therefore this is going to be equal to the right hand side here. Alright? So I can just write d1 of s, d2 of s, x2 is equal to this term, b3s, times d1 x1, which is going to be the right hand side. As I told you, you can extract x1 from the second equation, and then you can substitute it here. This is my alternative calculation here, which I like better. Okay? But you can do what I told here instead. So b3 of s times, there is going to be a parenthesis here, k1 gamma x0 plus b3s x2. Okay? Maybe I can get rid of these equations as well. I won't need them anymore. So now I have an equation which has the only variable x2, x0, and x2. And for the transfer function, I need to find the ratio of x2 to x0. Okay? So therefore, I'm going to first pass all of the x2 related terms to the left, and x0 related terms will remain on the right. Okay? So I have d1 of s, d2 of s. I will take this x2 related term to the right. And what is the multiplier? What is the coefficient of this x2? There is b3s here, and there is b3s here. Minus b3 square, s square, times I have x2 here. That is equal to, the only remaining term on the right hand side is b3 s k1 gamma x0. So now I can easily calculate what this ratio is. G of s is going to be ratio of x2 to x0 x2, take this x0 to the left and take this term to the right by dividing, then you're going to get b3 k1 gamma s divided by d1 of s d2 of s minus b3 square s square. This is my transfer function. And what are d1 of s and d2 of s? They are second order polynomials given by these equations. Okay? So now what is the order of this system? So when you look at a transfer function, you can actually tell what the order of that system is. Okay? And how do you do that? You look at the denominator. What is the highest power of s that you see in the denominator? That is going to be the order of this system. Here you cannot do it looking at the differential equations, because there is not a single differential equation here. There are double differential equations, and you won't be able to decide on the order of this system by looking at those differential equations. But in the transfer function, it is clearer. Okay? What is the highest power of s that you have in the denominator? Here, d1 and d2 are second order polynomials, and when they are multiplied, the largest power of s is going to be s to the power 4. Okay? So from this one, there comes an s to the power 4, and here there is an s to the s square. So therefore, the largest power of s that you get in the denominator is 4. So this is a fourth order system. Okay? And this is going to be useful for our writing the state space representation of this system. So now comes the final part of this example. Okay? And that is going to be the writing the state space representation. So how many state variables would I need in my state vector? I'm going to write a state space equation in the following form. X dot is equal to ax plus bu, y is equal to cx plus du. So I have here my state space representation. Okay? How many state variables would I need? And in this case, you need to say that we need 4 state variables, because the order of the system is just 4. Okay? So I'm going to define a state vector with 4 elements. Okay? I need to choose 4 variables from the variables in the system, and that is going to constitute my state vector. All right? So what can I select as my state variables? So whatever I select, I have a constraint in the state equation. What does the state equation tell us? It tells us that I need to be able to write the derivatives of those variables as a linear combination of the state variables and the input. Okay? I need to be able to write the derivatives of the state variables as a linear combination of the state variables and the input. So the first thing that I'm going to choose is going to be x1. When I put an x1 here, I need to be able to write x1 dot as a linear combination of the state variables and the input. So in order to be able to write x1 dot as a linear combination of the state variables, I'm going to add here x1 dot as well. Okay? Then what is going to happen? I will be able to write x1 dot as a linear combination of the state variables, because x1 dot is an element of the state then. Okay? And since I put here x1 dot, I need to be able to write the derivative of this variable as a linear combination of the state variables and the input. And I have x1 dot here. Its derivative is x1 double dot. I need to be able to write x1 double dot as a linear combination of the state variables and the input. So you see here our first differential equation. It expresses x1 double dot as a linear combination of x1. So this x3 is nothing but the input term. It is gamma x0. X0 is the input here. So this is state variable currently. This is state variable. Sorry, this is input. And this is state variable, x1 dot. x1 dot is the state variable, but I need an x2 dot in order to be able to write x1 double dot in terms of as a linear combination of the state variables. So I put here an x2 dot, okay? And then if I put the state variable here, then I can write x1 double dot as a linear combination of these variables and the input. What about x2 dot? Then I need to be able to write the derivative of x2 dot as a linear combination of the state variables and the input. The derivative of x2 dot is going to be x2 double dot. Look at the second differential equation. x2 double dot can be written as a linear combination of x2 dot, one of the state variables, x1 dot, one of the state variables, x2 dot, one of the state variables, and x2. This is not any of the state variables, and this is not any of the this is not the input. Okay. So what do I do here? I just add x2 as a state variable here as well. Okay, so then we have completed our 4 variables, and while trying to select these variables, I have made sure that I can write the derivatives of all of these variables as a linear combination of these variables plus the input. Okay? So now I'm ready to actually be able to write the state equations. So I have x dot is equal to, I will have a 4 by 4a matrix here, x plus a 4 by 1 b vector, u, and y is equal to c times x plus d times u. So now x is this one, okay? So I have here x dot. What is x dot? x1 dot, x1 double dot, x2 dot, and x2 double dot. And this x here is x1 dot, x2 dot. Okay? What is the input? Input here is x0. And what is the output? It is the displacement of the second mass, which is x2. All right? Let us first handle the easier one. So what is the c vector in this case? So the output is one of the state variables. So the input contribution is going to be 0 in the state in the output, and since x2 is the third state variable, I will have here 0 times x1, 0 times x1 dot, 1 times x2, plus 0 times x2 dot. So we have found the output equation in this case like this. So this is my c vector, and this is d. Again, it is equal to 0, because in our output, there is no direct input term. And now let us write the more difficult parts. So the state equation, let us find a and b. So here, for the first row, I need to express x1 dot as a linear combination of state variables and the input. But x1 dot is just one of the state variables. Okay? So the input contribution is going to be 0, and x1 dot is the second state variable element, second state vector element. So I will have 0, 1, 0, 0 here. And x1 double dot, I need, for the second rows, I need to express x1 double dot as a linear combination of the state variables and the input. For that, I'm going to use this first differential equation. Okay? x1 double dot is, what is the coefficient of x1 in x1 double dot? x1 is here, and there is no other x1, okay? So the coefficient is minus k1 x1, but in order to be able to express x1 double dot, I need to take this m1 multiplication to the right by dividing both sides by m1. So the coefficient of x1 is going to be minus k1 over m1. Minus k1 over m1. What is the coefficient of x1 dot inside x1 double dot? I am looking for x1 dots here. I have here and here. So I will have minus b1 plus b3 divided by m1. Minus b1 plus b3 divided by m1 here. What is the coefficient of x2 in x1 double dot? I'm looking for x2 on the right hand side. There is no x2 here. So I will put a 0. And what is the coefficient of x2 dot inside x1 double dot? x2 dot is here, and this is the only one, as you see. So that is plus b3 divided by m1. What is the contribution of input x0 inside x1 double dot? Here on the right hand side there is no input term, but there is x3. x3 is related to the input, so it is gamma x0 here. So the coefficient is going to be k1 times gamma divided by m1. k1 gamma divided by m1. Okay? So now let us try to look at the remaining. So I have x2 dot, which is one of the state variables here. It is the last state variable. That means that x2 dot is going to be 0 times x1, 0 times x1 dot, 0 times x2 times 1 times x2 dot, and there is no input in this equation. And we have a final row here, and that is the expression of x2 double dot in terms of the state variables and the input. x2 double dot can be expressed in terms of those variables by using the second differential equation here. So let us look at the coefficient of x1 in x2 double dot. So I'm looking for x1 on the right hand side. There is no x1, so I have 0 here. Coefficient of x1 dot, there is one here on the right hand side, and this is going to be plus b3, and I need to divide by m2. b3 divided by m2 here. And that is going to be plus because of the cancellation of these minus signs. Now the contribution of x2 inside x2 double dot is going to be this one, x2. So I have minus k2 divided by m2. And finally, contribution of x2 dot inside x2 double dot. x2 dot is here and here, so we have minus b2 plus b3 divided by m2. Minus b2 plus b3 divided by m2. Okay? So that is going to be, sorry for my terrible writing. And what about the input contribution in x2 double dot? In x2 double dot, there is no input term appearing on the right hand side. As a result, I need to put here 0. So that completes the state space representation for this system. So what did we do in these two lectures? So we have seen the differential equation, transfer function, and state space representations. And we have seen translational mechanical systems, and we have seen those components, in addition to electric circuit components, and we have obtained mathematical models for those. We have seen how to obtain state space equations and how to choose state variables here. So I hope that these are clear. So if these are not clear, please let me know so that I can actually try to explain more in additional lectures. So as you see, this was quite tiring. I'm quite tired now. But not all examples are this complicated, and once you get used to this type of calculations, it becomes easier and easier as time goes by. So that is going to be all for this lecture. So thank you for tolerating me, and I hope you will watch the future lectures. Thank you. Bye-bye.